Markov decision processes, and we're trying to estimate them, but we are going to sort of dive into model-free stuff. So everything we've done so far has been, so before, we knew the model, so we knew the probabilities. So a good example is in snakes and ladders. We knew that we rolled a 6-sided dice, and we knew that all the sides were equally likely, and we used that to solve the problem. But imagine you were playing snakes and ladders, and you didn't get to see the dice, right? Like you're playing snakes and ladders, and someone was just like, you rolled a 3, and then you move. Like you don't know if it's a 6-sided dice or a 20-sided dice or whatever. So now we are doing, quote, model-free, which means we don't know the probabilities beforehand. Don't know probabilities. What we do have access to is we can like sort of simulate what's going on. So we can sort of sample what's going on. And we're going to sort of replace our knowledge of the probabilities with samples and see how we can update our methods. Can sample what happens. A good example of this is if you were going to build like a robot arm. Well, there's two sort of ways you could do it. You could work really hard to say like, oh, my robot arm, when you apply this motor at this angle, it does this, right? And like really figure out a really complicated like mathematical model for how the robot arm works and like where it's going. Or you could just say, look, here's a robot arm. The things you can do is you can put this motor on or that motor on. Now go. And you could try to figure things out that way. And it turns out that this model-free way for a lot of problems is a lot better. There's two advantages. So one is you don't need to know the probabilities. And the other advantage is it can work if the state space is very large. It can work for very large state spaces. And sort of the reason is that the probabilities depended on these matrices, M, which were roughly number of states by number of states. I'm going to write squared because I'm running out of room here. So if the number of states is some huge number and you square it, that's huge. Like this matrix is too big to store. But when we're learning this thing, we're going to only learn value functions and Q functions. So we're going to know V of S and Q of S. A are learned directly. And that's a lot easier because it's only the number of states, not the number of states squared. Later on, we're going to see that even better. You don't need to keep track of every single state. You can make the value function be any function you want. So maybe you just keep track of some coefficients and do like a linear regression to learn the states, or you can use a neural network or something. So anytime you can represent the function on your state space, then you can do it this way. Whereas if you want to do it really with the way we did it before, you really need to know the number of states squared. So you imagine for something like chess, this would be impossible because it's way too big, but this kind of thing is definitely possible. So we're going to move towards learning model-free stuff, and we're going to see that everything we learned before is going to help us understand this. So this was kind of mentioned in the video, model versus model-free, and that's the direction we're going. Were there any other questions or comments about anything I've said or the video or where we are? Okay, and we're going to use, was there a question here? No? Okay, so the thing we're going to do is Monte Carlo stuff. Monte Carlo. This is what we're going to start with, and we're going to improve from there. Monte Carlo, also known as MC, which is on the board, MC. What is Monte Carlo? Well, Monte Carlo is a city or something in Europe where they have a big casino, and people go there. So why do we call these methods Monte Carlo? They are methods based on randomness. So method to find a non-random answer using random, I'll call it random stuff to be very general. Okay. That's what Monte Carlo means. So it's kind of a weird name that this method to find a non-random answer using random stuff was given a name. It was named after a casino, but I guess it kind of makes sense because the casino works. There's also something called a Las Vegas algorithm. That's something else. I don't know exactly what a Las Vegas algorithm is, so let me not say it wrong. You can Google it on your own time. I think in a Las Vegas algorithm, you find a random answer using random stuff. So the important thing is the Monte Carlo, at the end of the day, gives a non-random answer. And let me give you an example. here's an example. This is my favorite example. Let's pretend you wanted to know pi, right? You want to write a computer program that calculates pi. One way is you could go to a calculus class, learn some formulas for pi, and then like add them up. But we're not going to do that. We're going to do a Monte Carlo way. So here's my Monte Carlo way to do pi. I'm going to estimate pi, this pi, 3.14, ... Here's what I do. I draw a square. And then I'm going to draw a little quarter circle in the square. And then what I'm going to do is I'm going to take random points in the square. So let's draw a bunch of random points. I'm going to draw them as little dots. So here's some random points in the square. So I'm assuming I have access to a computer that can make random points in the square. Okay, so I have a bunch of random points in the square. I have my quarter circle. It's easy to check if a point is inside the quarter circle or outside the quarter circle, because it's inside. If you take x squared plus y squared, you can check if that's less than 1. So in circle means that x squared plus y squared is less than 1. So you can get the x and the y coordinate randomly. That's a random point in the square. You can check is it inside the quarter circle or not by doing x squared plus y squared and checking is it less than 1. So finally, here's my estimate for pi. Pi is approximately the sum of the points inside, n equals 1 to, let's call it capital N samples of points inside. So let's say, let me do it this way. Let's say 1, I'll do the indicator function of x n squared plus y n squared less than 1. So the indicator function means the function that is 1 if x n squared plus y n squared is less than 1. That's saying if the nth point is inside the circle, you get a 1. If it's not inside the circle, you get a 0. And then I'm going to divide by the number of samples. And so this will count the number of points inside the quarter circle divided by the total number of points. And that is going to estimate pi. Why is it going to estimate pi? Because this is approximately the area of the circle divided by the area of the square. It's going to estimate the thing. So this is a Monte Carlo algorithm. We're using random samples to estimate pi. So it's a non-random answer. Like pi is a non-random number. We're trying to estimate it. And we're estimating it by using a process involving randomness, which seems pretty counterintuitive. Why would you do that? It makes a lot of sense in our situation because our things involve randomness to begin with. So we're trying to find the optimal strategy, the optimal value function, things like that. Those involve some expected values. It's not surprising that you do it. This pi one is a little more surprising, but we can learn from this one. There is one thing I'm missing on the board here. So there's a small mistake. If you do this, you won't get the right answer. Yeah?
The indicator function can only be 1, right? So when you're calculating this, there's no way for it to give an answer greater than 1, right?
That's right. That's right. So this number, this is a great point. So I'm adding up a bunch of things that are either 0 or 1, either inside the circle or outside the circle. You add up n things, capital N things that are inside or outside, you get a number between 0 and n. If they're all outside, you get 0. If they're all inside, you get n samples. Then you divide it by n samples. So you're going to get a number between 0 and 1. But pi is not between 0 and 1. So there's some kind of issue. What is the issue? Yeah?
Because this formula estimates quarter pi.
That's right. This is for the quarter circle. So to fix it, why don't we put in a 4? Let's put in a 4 here. So I'll give you 4 points if you're inside the circle, and 0 points if you're out of the circle. And then it'll really be the area of the circle, which actually will appear as 4 times the area of the quarter circle. So that's the quarter circle. The whole circle is something like this. And to fix it, I just multiplied everything by 4. So times 4 to get the... So I'm sort of like pretending, I'm doing the quarter circle, and I'm pretending I have a whole circle by multiplying it by 4. That's an easy way to fix it up. You could also like sample points from -1 to 1 instead. So here, x and y are between 0 and 1, and that's how it works. So this is a Monte Carlo algorithm. Any questions or comments about the theory? We're about to go to seeing this in code and making some comments there. Okay, let's see it in code. So here it is in code. Monte Carlo, and we have this function called my dice roll. But I wanted, let me see if I can find the version that has pi. I put that in, Monte Carlo. Okay, here this is what we gotta do. We gotta go open up a new collab. So I'm sure this exists. Okay, all right, we're gonna do it. We're just gonna do it live. So when I programmed this originally, I used a dice roll, which is a number between 1 and 6. But the pi is more fun. Let's do the pi. So let's do it. It's still gonna be called my dice roll. And you should think about it as like every time you throw a thing, you're either in or out. That's your dice roll. So I'm going to make an x, which is going to be a random.randn, and y, which is a random.randn. And then I'm going to, or you say in the quarter circle, that is x squared plus y squared is less than 1. And then I'm going to return 4 times if you're in the quarter circle. Okay, let's see if this runs. Ah, you have to log in. Okay. All right, there's your problem. No wonder it couldn't find the other files I had. Okay, let's try again. All right, stand by while I annoyingly do this. Did I not press the right button or something? Sorry, guys. Okay. Not now. Ooh, that's my problem. Okay. Now will it let me? Okay. Here we go. Here's the one with it should have. There we go. My dice roll. So we have a function called my dice roll, which is actually exactly what we did before. X and y are random from the square, and then 4 times whether or not you're in the circle. All right. Now let's run this one. So import numpy, and this is going to be called my dice roll. So you really think of it as like we did one experiment. That's my dice roll. It could be an actual dice roll, or it could be some other process. And then here's the simplest method that I described to you before. And what I'm doing here is I have a total variable, and then I'm doing n is the number of samples. Here it's 1,000,000, 10 to the 6, and I just do a loop, and I'm adding up the sum of my dice roll. So every time you run it, you get a new dice roll. And at the end, I estimate the mean, and then I do total divided by n, and then I print out what it is. And I got this, 3.14196. Is that pi? Well, the first couple of decimals are right. 3.14 something. That's pi. So we basically just did exactly this algorithm. And that's the simplest version. So we could just take this and start doing reinforcement learning stuff, learning about the value function and things. But I want to work on this, and I want to like soup it up a little bit. So that's why the file is called Monte Carlo Improvements. We're going to fix this thing up quite a bit. And the first question is to understand the dependence on n and how good our final answer is. So you see this final answer is not perfect. And my question is, what is the relationship between the number of samples and how good the answer is? And I put this in a Mathmatize for you, which is the next Mathmatize. So the number of samples. Imagine you are using Monte Carlo and you want to estimate the mean of a dice. So before I was doing this pi thing on what we're about to run. You guys are going to tell me how many rolls to do. And I am going to run the other one, the regular dice, a regular 1 to 6 dice, and we want to estimate the mean of the dice. So this is like, imagine somebody gives you a mysterious dice on the street, and they're like, ooh, look at this mysterious dice. Please figure out what the average of this dice is. And you can't look at the sides. The only thing you can do is roll it over and over again. Okay, and the question is, how many times do you need to know, how many times would you need to roll the dice to estimate the mean to an accuracy of 0.001? So I'll tell you, it's, you know, you're supposed to pretend you don't know this. It's actually an ordinary 6-sided dice. So the average is 3.5. But how many dice rolls do you need to get it 3.5 within 0.01? Do you think you need 1,000 rolls, 10,000 rolls, 100,000 rolls, or 1,000,000 rolls to estimate it to that accuracy? This is 1 over 1,000. And I'll let you think for a few minutes here. How many do you think you need? And really imagine you're on the street, you're like sitting there rolling dice. Like imagine it costs you a little bit of money to do these. You want to kind of do the minimum number to get the accuracy you need without like overshooting it. Of course, if you did the maximum number, you would probably get it. But what is the minimum you would need? Okay, I'll give you a minute to think about that. Okay, I have 14 people. Who needs more time to think? Okay, put in, if you're not sure, put in a guess. 5. Okay. Wait for the last couple people to get in here. Okay. Again, this question is super relevant for exactly what we want to do because we're trying to estimate the optimal value function for things, and we're going to want to know how many simulations to do. If you're doing something with like a physical robot arm, like there's people who have labs with physical robot arms and they do this, if it takes 1,000,000 samples of your robot arm moving around, that might be too many. Like you might not finish in a reasonable amount of time. Whereas if it only takes 1,000 robot arm movements, that can make a big difference. So this kind of question is super, super real life and super important. Of course, we're doing kind of an easy version of it here. Let's see what people said. All right. So 3 people are in 1,000,000, 4 people are in 10,000. 9 people are in 100,000, and 3 people are within 1,000. Okay, let's try 100,000. That was the most common with about half the people, but it's still pretty split. Let's try 100,000 and see how close we get to 3.5. Okay, so let's try it. Monte Carlo improvements. So I'm going to run this dice roll function. So now my dice roll is really a random dice between 1 and 6, written with a 6 plus 1, so you don't get screwed up by the thing, and we're going to do 100,000. 100,000. Can you put a comma in? I don't know. Let's
Underscore.
not. Underscore. All right, thank you. Let's just see this. So, if you guys are right, we should get 3.51 or 3.49, right? That would be right. Let's see. Did we get it? 3.492. So very good. It was. Wait a second. That's not right, right? I want it to be right within 0.001. And we're off by 0.08, right? The real answer is 3.5 exactly. You guys told me the answer is 3.492. So we're off by 0.08. That's 8 times bigger than what we wanted, right? So if I was, let's take an example. Imagine you work at Boeing and you're putting a door on a plane. And someone is like, make sure that you're up within 0.001. You're like, no problem, I got it. 0.08. No good. Bad. So, you guys got the wrong answer. You got the wrong answer. I'll let you think about it a little more. We're going to re-vote. I guess there's only one thing it can be. I'm going to let you think for a second. We're going to re-vote and think about why 100,000 is not enough. There's a simple math calculation you can do to make it work. But let's duplicate this and run it again. Okay, so I opened it back up. Have another minute to think See if you can explain why it should be something else. Okay, time's almost up, I guess. Maybe this was a little anti-climactic the way I did it, but let's see what you said. All right, great, everybody's in a million. Okay, right, 100,000 wasn't enough. How many do you need? Well, it needs to be more than 100,000. The only option on here that's more than 100,000 is a million. If you do a million, let's see what happens. And a million should work. So a million, I guess, is like this, a million, and then we run it. So 10 times as many samples. Of course, this time it takes longer. But now 3.501. Okay, I guess it's a little bit more than 0.01. But maybe it'll keep the plane on the door. Or the door on the plane, rather. Let's try it again. So before it was 0.501. Now it's 499,248. So now it's close enough. So the difference between the true answer and what we have is approximately what we want, which is 1 over 1,000. And I heard some people grumbling about stats class. If you had a good stats class, there's something special about this number that you will automatically know just by looking at this number that the kind of order of magnitude you're off by will be what we want, 1 over 1,000. There's a special secret formula. And if you only know one thing about Monte Carlo, you got to know this formula, which is how big is the error versus the sample size. This is the most important thing about Monte Carlo. How do I write the most important thing? I guess I'll just say the most important thing. The most important thing to know about Monte Carlo. Okay, and that is, what is the relationship between the error versus the number of samples? Okay, because Monte Carlo, unlike regular algorithms you learn in computer science class, Monte Carlo algorithms are random and they don't give you the exact answer. They will always have some amount of error, and you can control that error. You can make it smaller by increasing the number of samples. But it's very important to know how big the error is versus the number of samples. If you don't understand that, then either you're going to get errors that are way too big, or you're going to spend way too much time doing more samples than you need to. So if you want to use Monte Carlo effectively, you need to understand this. And there's a simple rule. I'm going to write it like this. The error is approximately, or maybe like approximately equal to, something involving the number of samples. Does anyone want to take a stab at what is that something? Yeah?
1 over square root of n.
1 over square root of n. That's exactly right. The square root of n samples. And this comes exactly from stats, and specifically from the central limit theorem. The central limit theorem of stats. And 1 over square root of n is the approximate standard deviation. I'm going to write, let's write SD for standard deviation of the sample of the mean. So when you compute this mean, on average, the Monte Carlo algorithm will give the exact right answer. So sometimes it gives a little bit more than 3.5. Sometimes it gives a little less than 3.5. And how far away it is from 3.5 is given by the standard deviation, which by the central limit theorem is 1 over the square root of number of samples in magnitude. So I think the most accurate thing you can say is that it is big O of this. So some constant times that. And actually in this simple case, I can tell you exactly what the constant is. The constant will be the standard deviation of the true thing. So I'm going to write standard deviation of one outcome. So in our case, the actual difference is the standard deviation of one single dice roll divided by the square root of the number of samples. And that is why you need a million. If you want to get within 1 over 1,000, you need like on the order of a million. If you have something that's very chaotic and is all over the place, you need more than 1 million. If it's almost always the same number, then you need a little less than 1 million, but the order of magnitude is 1 over 1 million, or 1 million samples to get a 1 over 1,000 accuracy. And this square root is really important. So first improvement, this is good. Let's make a version of the Monte Carlo algorithm that doesn't just output an answer, it outputs upper bound and a lower bound, and it says, I think the answer is somewhere in there. This is an improvement because you can get a sense of how big the error is, right? So when you run it, if you don't know the true answer, you won't know how far away you are, but you'll say, like, I think it's between this and that, and you'll go, oh, that's way too big. That's 0.08. That's way too much. We need to run more. So this is improvement number 1. Improvement number 1 is estimate sigma. Let's not use the word sigma. Let's call it SD of one sample. One sample. And you can create a confidence interval. Okay, I shouldn't use confidence interval means like some specific thing in stats. So I want to make an interval in which I'm confident the answer will be in there. That might not be called a confidence interval. So let's not use the words confidence interval. Let's use create estimated region or something. An estimated region. It might be a confidence interval, but I don't want to avoid this debate. An estimated region where the answer lies with high probability. The answer lies with high probability. And the way we're going to do it is we're going to have estimated upper. I'm going to call this upper. And mu lower. And mu upper and mu lower, they will both start with the estimated mean, which is, okay, I'll call this mu hat. Mu hat. I'm going to put all these hats on, and then I'll tell you what it means. Mu upper is going to be the mean we had before plus 2 times the standard deviation that we estimated divided by the square root of the number of samples. And the mean lower will be minus 2 times the standard deviation divided by the square root of the number of samples. Okay, so what are these hats? These hats might give you some flashbacks to stats class. Hat means estimated. So we never know the true mean. The true mean is 3.5. We can't look at the dice and figure out the true mean. We can estimate the mean. The mu hat is our straight estimate, is this formula, the sum divided by the number of samples. So mu hat equals the sum of thing I divided by the number of samples. This is sometimes called the empirical mean. Empirical means did with an experiment. We're going to estimate the SD as well from the samples. So using thing I, we're going to estimate SD. And then we're going to come up with these upper and lower estimates. And we hope that with high probability, the true answer is somewhere in that interval. And this is much better than just having a mu hat, because now we have a sense of how accurate we are. If this interval is way bigger than we need, then we know we need to run more samples, and we can sort of be efficient with our samples. So that's the idea. Questions? Yeah?
Yeah, where's the 2?
Okay, great. So the 2, I'm doing a 2 standard deviation interval here, and that will encapsulate, in some sense, 95% of the probability distribution. You can put any number you want here. The bigger you make it, the more confident you are that the answer is in the region. And yeah, there's some stats class on 2 becomes a 95% confidence interval in some sense. So you can map from how big this number is to how likely it is. And people usually use, technically it's like 1.96 to get 95%. But using this 2 will be, in some sense, 95% sure it's between here and here. If you actually want to make a real statement, there's a whole bunch of other assumptions and things you need. But like very roughly speaking, that's a true statement. Okay. Great question. Any other questions? Okay, let me show you how you could do this in code. What you have to do is you have to estimate the standard deviation, which is, again, something you can do in stats class. But here is the estimate for the standard deviation. We're going to use the standard deviation is approximately the sum of the squares of the things, 1 to n of thing I squared minus mu hat over n. So you can estimate the sum of the squares of the things. You can subtract the mean squared, and that will be the variance. I want the standard deviation, so I'm going to do the square root of all this. Okay. And so this is coming from the formula that the standard deviation is the square root of the variance, which is the square root of the expected value of x squared minus the expected value of x squared. So this is like bread and butter stats class stuff. We're estimating the expected value squared by adding up the thing squared. We're estimating the mean, and then we're combining them to get an estimate of the standard deviation. Let's see what this looks like in code. I think I have this one here. All right, major error analysis improvement, estimate the variance and use the central limit theorem. That's exactly what we're doing. So same exact process as before, but now instead of just keeping track of the total, I have another variable called the total square. And then I keep track of the total and the total square. I estimate the mean, I estimate the variance, and then I make these two things, which are the upper and lower estimate. I'm using 2, so they're 2 standard deviations away. Let's see this one run, and let's do a million again, just for fun. Okay, and we're doing an actual dice roll here. So it's going to be 3.5 and a little bit. Okay, so our estimated for the mean was 3.5002. In real life, we wouldn't know the true answer is 3.5. So just looking at that, we don't know how far away we are. Our estimate for the variance is 2.917. You can calculate for an actual dice, you can calculate exactly what the variance is. I believe it's like 30 divided by 6. Anyway, it's close to that. And now we have an upper and a lower estimate. Our upper estimate is 3.503, and our lower estimate is 3.496. So we're kind of pretty sure that the real answer is somewhere between 496 and 503, even though we don't know exactly what it is. So you should kind of ignore the real estimate. You should think of it's some number in this range. That way you can get a sense of how close you are. So actually, if you wanted to get within 0.01, we have to run even more samples. Like, it's true that it's within 0.01, but you can't be sure. You need to run even more if you want to be 95% sure. Okay, this is a major improvement. You must know this one. Questions or comments about it? This is like stats review. Okay, here is the other thing, and this is like the computer science way to improve it. So we improved it. Now we understand how big our error is based on the laws of statistics and probability. But now we're going to do another improvement, which is to do a computer science improvement, we're going to use vectors. And when you do vectors, instead of having a for loop, so here's a for loop that runs 1,000,000 times, I'm going to do it all in a big vector of size 1,000,000. So my code won't have a for loop. It'll say, make a vector of size 1,000,000, then do something with the vector. Here's what the code looks like. So first of all, I changed the generating one dice roll at a time. Instead of generating one at a time, I put in size equals n samples. And NumPy will give me now a big vector, which is 1,000,000 long, of dice rolls. So before I had to run this function 1,000,000 times. Now I run this function once, but it makes a long, long vector of size 1,000,000. And then, here's how I estimate it. I do the mean, and I just print the mean. No for loops. This speeds it up by a little bit. This is a small computer science improvement. I want you guys just thinking in terms of vibes. How much faster will this be? So we're going to run it in a second. I'm going to run classic version with loops versus no loops. How much faster do you think it is? Okay, I'm going to stop it when it gets to 1 minute. So 15 seconds left. Put in your guess. Of course, you have no way, unless you've done this experiment before on your own, you have no way to know how to speed it up. Okay, I said I'd stop in a minute. Okay, let's see what you said. We're going to try refreshing it because it didn't work. Perhaps I have lost the internet. Okay. this one. Reveal counts. Okay, there they are. Okay. So pretty split all over the place. Let's see what happens when we run it. Okay, and like I heard somebody say, it's not magic. Like it still has to do the calculation, right? So here it is. I'm going to use this time thing to do it. So if you put in percent time, that's called cell magic, and it will run some extra stuff. In this case, if you put percent time, it'll time how long it takes to run everything and tell you how long it takes. So we're going to compare this one to the original one we started with. So I have a little cell magic over here. 1,000,000, doing it the classic way. Let's see how long does this take. So here it says it took CPU time, it took 3.23 seconds. The system was also laggy for 5.3 milliseconds. So the total is 3.25 seconds. 3.25 seconds. How long will this thing take if we do it with vectors? So first of all, let's make sure we run everything. Oh, I guess I can run before, and it'll run everything before. Let's make sure we do that so that it knows what function the function is. Oh, okay. I guess we have to wait for this thing. Okay, there we go. Okay, so we're going to run this one, my vector dice roll, and then we're going to do it time. Okay. How long did it take? 14.2 milliseconds. So before it took 3.25 seconds, now it took 14.2 milliseconds. Again, the computer was delayed by 4 milliseconds. Before the computer was delayed by 4 milliseconds, we were like, okay, well, that's like a rounding error. Now the computer being delayed is like a quarter of the time it took. So how much faster did it go? 3.25 seconds divided by 15 milliseconds is a factor of 216 speed up. So the computer did it 200 times faster by doing it in vectors. Why is it so much faster? Why is it so much faster? Because it's like, again, somebody pointed out, it's not magic. Like it still has to do all the calculations. It still has to generate all the dice rolls and add it up. The reason is modern computer architecture, modern CPUs, can do more than one thing at once. Okay? You can tell it, you can give it a bunch of stuff, and it can work on all the stuff at the same time. When you do a for loop, you are wasting that potential. So in the for loop, you are telling it, please do it once, and then when you're done, do it again. And then when you're done, do it again. So it has to wait until it finishes the first calculation to do the next calculation. When you do it in a vector, the computer architecture is like highly optimized, and it knows the right way to split it up into chunks so it can do a bunch at once. So it'll take like the first 1,000 and it'll work on those, then it'll take the next 1,000 and work on those. And if you just tell it exactly what you want as a vector, it can sort of optimize itself in a much smarter way. That's why it runs hundreds of times faster. So it's a good pro tip to know when you're doing this stuff. If you can write your code to be vectors, it will literally be hundreds of times faster. It's the difference between waiting for a minute for your code to complete and waiting like several hours. So it's really good to know. It really makes certain things possible that were not possible before. Any questions or comments? Yeah?
One comment about vectorization is that memory.
Yes, okay, this is a very good point. So if you do it this way, memory is not an issue. If you do it the other way, if you make n big enough, eventually it will yell at you. Let's see how big we have to make n for it to yell at you. This is a great point. Online, this is not what I want. I want vector. Okay, yeah, here, let's add 3 zeros. I think it'll still work. Okay, I guess it'll take 1,000 times longer, so it'll take like 15 seconds. So eventually, if you make the number big enough, it will yell at you and say, like, I ran out of memory. I cannot store a vector that big. The optimal thing you can do when you're running this kind of algorithm is make it big enough so it takes up the entire computer memory and run that. And then if you want even more samples, then run it like with a for loop. So do it with a for loop where you take up the entire computer memory at each time. That's the optimal way to do it. Then you're not wasting any memory. Okay, so it still ran it with 1 billion. Eventually, it'll stop. So running 1 billion took about 3 times longer than running 1 million before. Okay. So eventually you will run out of memory, then you back it off a little bit. Question? Yeah.
In the vector way that we did we call the function that was making the vector in our timed one, or did we call it in the block above?
No, we called them, it was called as part of the time, yeah. So, and another part of the speed up is the function that makes the random samples is also faster when it's vectorized. So if you tell the computer, please make 1 million random dice rolls, it will be faster than saying make one dice roll 1 million times. And in some situations, it is trickier to write the code to generate the random sample. Like imagine it was more complicated than just a single dice roll. Then you would need to like convince the computer to have these vectors floating around. For an example of this, you can go look at the final project code. In your final project code, I have it set up so you can play a bunch of games of Easy 21 at the same time. So instead of just playing one round at a time, you can play 1,000,000 rounds at once, and that will help you guys do Monte Carlo faster. But yeah, that's a fantastic question. Anybody else? Okay, so those are the two major improvements. There are some other minor improvements. Well, one thing is you can do the vector speed and the errors. You can estimate the mean and the variance, and then you can do the upper and lower estimate. Of course, it runs a lot faster. Here is another improvement, and this one is important to know because it is used a lot in this reinforcement learning book and all the algorithms we're going to do. And it's called an online algorithm. Online is an unfortunate word because online makes it sound like it's connected to the internet. That is not what it means. Online has another word, another meaning. Online algorithm means something else. Does anyone know what online means? So online, when you see an online algorithm, it means it's running as it goes. So these algorithms, they are what we've done so far. Let's go to the very first one. This is not an online algorithm because I first calculate this total, and at the end, I do something to the total to get the answer that I want. So sort of like I do a bunch of stuff, and then at the end, I have to do some work to fix it. An online algorithm is one where it does the work as it goes. So it's always doing the work, and then at any time you can stop it and say, like, what is the estimated mean without having to divide by n. Here, dividing by n is kind of like an easy step, but online algorithms, they work as they go. And here is the online algorithm for calculating the mean. Let me write it out on paper, because I think it's a little easier. So, okay. So this is the next little thing we're going to do, is an online algorithm for the mean. Okay, and then I'll start by writing out what is the not online. Not online. So here you make total equals 0, then you loop over xi, let's call it, and then you say total plus equal xi, and at the end you mean is equal to total divided by n. Here is the online version. So the answer at the end will be the same exact thing, but I won't have to do a step at the end. As I go, I will do it. So I won't have a total. I'll just have mean. Mean is going to start at 0, and I'm going to loop over the xi. And here is the very funny formula that is not so hard to figure out why it works, but is a little bit magical. Let me write it out in purple. Mean is plus equal to xi minus mean. Okay, if you just had this, if you just did mean plus equal xi minus mean, you're adding on to the mean, you're adding on xi minus the mean. Well, the minus the mean would cancel out the mean, and at every step, mean would be equal to xi. So if you added up these differences like this, as written, it's just outputting the ith sample. If instead you add in one little thing, you just say 1 over I, then it will output the exact mean. So what this is doing is, the very first step, after one step, mean will be equal to x1. After 2 steps, you'll take x1 and you'll add on 1/2 of x2 minus x1. And then it will be equal to x1 plus x2 divided by 2. And if you just check like some basic arithmetic, at every step, the mean is equal to the sum x1 plus x2 plus dot 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 plus xn divided by n. So this like 1 over I is the exact right thing to add on to make it equal to the mean, which is kind of surprising. But it's a fun, if you want to check, you can check using algebra. Check with simple algebra, this works. Okay. So this is called an online algorithm because you calculate as you go. If you imagine pausing the algorithm at any time, it will have a partially correct answer. Whereas if you pause this one in the middle, like you don't know how many you have to divide by. So it won't give you a correct answer. This one works. So that's called an online algorithm. And I think I have it in the code. Here it is with a 1 over n. So I called it n instead of I, 1 over n times x minus the estimated mean. So that's nice for the mean. You can do the same thing for the variance. I will not go through the full details of this. There's a nice Wikipedia page on algorithms for calculating variance. And there's an online algorithm that does the mean and the variance. It looks a little scary. It looks like this. You have to do two things. There's something called M2. There's the mean. There's the M2. But it's an online algorithm, and it goes through, and it just calculates, as you go, the mean and the M2, and then it gets the variance at the end. So that's a nice one. The thing I do want to get to is this constant alpha average. And this is a thing that is really commonly used in reinforcement learning. And we're going to see a lot, and I want to show you what it is. So this was the not online way to do it. This was the online way to do it. Here is the constant alpha way to do it. The constant alpha way. What you do is you start the mean equal to 0, like over here. You loop over the xi's, and you set mean plus equal alpha times xi minus the mean. And here alpha is some constant. Alpha is some constant. Okay. Why would anybody do this? This one was perfectly correct. This actually gives the actual mean. This is going to give some kind of average of the mean that depends on the value of alpha. So it won't be exactly right. It depends on alpha. You can kind of get a relationship between what alpha means with 1 over I. So if you take 1 over alpha, that's sort of like the size of the number of samples you're using in some sense. People really love this algorithm. It has a couple nice advantages. The major advantage, if you're doing this, you just don't have to keep track of the number at all. So the major advantage, no I. So before you needed to keep track of what I is, how many samples you've seen so far. Now it's just some constant thing. And if you do this, you can calculate the average as you go. And people use this a lot. Okay. Any questions or comments about that? Yeah.
In the case where you do end up looping over every single xi,
Yeah.
would the non-online one technically be faster because you're only dividing once at the end, whereas in the online?
Yes.
doing it
Okay.
every
Yeah, you're thinking about like the operations of, like this one has like more arithmetic operations than this one. Yes, it's true. The thing that's like technically true. The thing is, on the computer, doing little operations like dividing or like multiplying are very fast. So you shouldn't worry too much about optimizing those. So something like, here's a thing that happens in real life. You're running your program and it crashes halfway. If you were running this one, now you're like, oh, start over. If you're running this one, if you can recover what the variable was, you still have somewhere to start, right? And you can even use it, like you can restart in the middle of your sequence.
Okay.
So another problem with this one, if you want to talk about technical CS things, is sometimes you'll get an integer overflow in this one, whereas this one won't have that problem because you always add on small differences. So this one is better in a number of ways. Same with this one. So that's why people like these ones. Yeah.
Well, but with alpha, wouldn't like some of the points, for example, like the initial points, wouldn't they be like very undersampled?
Yes, that's right. So essentially, what it does is, if you let let's call it m equal 1 over alpha. This is like the characteristic number of points you care about. And so if m is 1 over alpha, so let's pretend alpha is 0.1, and then m is 10. That's saying we kind of are averaging over the last 10 samples. Something that was 100 samples ago will barely count, because it's 10 characteristic number of samples before. And so this will sort of have a bias towards the most recent samples, and it will downweight the very old samples. That property is actually going to be good as we go, because you'll see that as you're doing these like learning algorithms, what you learn initially is kind of wrong, and then like you improve over time. So having this property that you sort of forget the far past is actually helpful. And if you want, people put alpha on a schedule. So they say, you know, we're going to decrease the value of alpha. It's a little bit like decreasing the learning rate in a machine learning algorithm, so that we get closer and closer. We increase the characteristic length as we go. Of course, if you make alpha exactly 1 over I, that's a schedule of the alphas, and then you get exactly the online algorithm. Okay. Why am I telling you all this? Now you guys have all the tools you need to do the Monte Carlo stuff. And we're going to go back to the video that we started with, and he's going to do an example with a constant alpha. Okay? And hopefully it will make sense. Okay. It won't make fully sense because I was hoping to give you guys the exact formulas, but let's watch it first and get a sense of it, and then I'll tell you the formulas. It's all in the video. Of course, the video is like 20 minutes and does like what I would do in 3 hours of lecture. So the level of detail is different, but we'll see how much you get. Okay, I want to skip over this part. There's some confusing thing. We want this. Okay, yeah. Okay, great. Okay, so here's what it says. Monte Carlo evaluation. This is what we're going to start with. Given samples under pi, so you have some fixed policy, like the hit under L policy, you want to estimate Q pi, or V pi, but let's say it's Q pi. Here's the thing. We're going to express Q pi as an estimation of some, okay, ignore this line. We're going to express the Q pi estimation as an average over the trajectories. So we're going to sample M times, and we're going to average them. And there's a nice example here. You'll see the formula, and you'll see the averages.
Trajectory samples of an MRP.
Oh, MRP is a Markov reward process. Before we had actions, right? Once you fix the policy pi, you only see actions. There's no actions anymore, right? So the policy pi determines all the actions. Now all you see are states and rewards, right? Once you've decided what to do, you run around the Markov decision process. All the decisions are made for you. You have rewards and states. That's a Markov reward process.
You can write one trajectory sample like this,
Okay.
where little m indexes from 1 to capital M. If you're also reading from the textbook, this is a little deviation from their notation. Okay, and that brings us to the main idea of MC. Use averages to approximate the policy's value function. Remember, the value of state S is the expected return when the state at time t is S. The idea is to approximate it with this. This is just the return averaged over all times S was visited in the data. Let's break it down. First, we're summing over all trajectories and each time step within those trajectories. This indicator selects out state S, the state whose value we're trying to calculate. This is the sample return at time tau from the mth trajectory. And that means this whole thing is the sum of all returns in the data that followed state S. Finally, CS just counts how many times state S was visited. And that gives us our estimate, VS. But there's an issue. To calculate this, we must process a batch of M trajectories. What would be better is if we applied an update rule after each trajectory, like this. Applying this is in fact exactly the same as calculating the average up to the mth sample. Here, C of SMT.
Okay, so this person was scared to say online algorithm, right? They're saying do it as you go. This formula that is written down is exactly the online algorithm version. So here it's doing the mean. It says add them up. So you want to estimate the return from some state, add up the total returns that you got in your entire sample from that state, divide by the number of times you saw that state. And here it's saying, okay, instead of adding it up and dividing, do the online version. As you go, do 1 over the number of samples and the difference. That little line there is exactly the online algorithm. Yeah?
Sorry, this might just be a little bit of a tangent, but
Yeah.
when it comes to, so given that you have a known policy that you're testing,
Yeah. Mm-hmm.
how does that, and so all the actions go away,
That's right.
but what about in situations where like a mixed strategy is...
Oh, the policy could be random. So so far in this, we've always talked about a policy as like you do X, but a policy could equally well be you flip a coin and then you do X with probability 50%. You do something else with
Yeah,
probability
because
50%.
you can imagine a situation
Yes.
where it's like if you wanted to do like rock, paper, scissors,
Mhm,
picking
yeah,
rock is
for
not
sure.
the-
Yeah. So this is a good point. The policy can be random, but it's a pre-specified randomness. And if you have that pre-specified randomness, what you do next will be random. But if you can just incorporate that randomness in which state you move to next.
Okay.
Yeah, that's a great question. Any other questions? Okay, so he has the online algorithm. You're going to see in a second he's going to replace the online algorithm with a constant alpha algorithm.
Counts all visits to the state up to time t of the mth trajectory. Now, if we were to plot this for one state over the episode index m, then we'd get something similar to this, which basically means we make smaller updates after we've processed more data. That makes sense, but we can actually change this to a constant between 0 and 1, and we'll still converge to the right answer. This is simpler to study, so we'll do that. That means we can change our update rule to this, where alpha is a constant we need to specify up front. This is called constant alpha MC, and alpha is called the step size. Let's get familiar with its behavior. Here, I have the episode index m, and over here, I'll be showing our constant alpha. Let's say the true value for some state s is this. Next, if we assume, just for explanation's sake, that state s is visited exactly once per episode, we can plot the returns. Now, using an alpha of 0.2 and applying the update rule after each trajectory gives us this. This is our estimate of state s's value as we process trajectories. As you can see, eventually converges approximately to the truth. Also, we can see the effect of alpha. If it's small, then the estimate takes a while to catch up to the right place, but it's accurate when it gets there. If it's large, the estimate gets to the right area quickly, but it's a noisier estimate. In general, the best choice of alpha will be problem dependent. All right, it's about time we do a multi-state example. This is example 6.2 from Sutton and Bardo. We'll be looking at a Markov reward process with 7 states.
Okay, so they're about to do an example where they're going to show you exactly the algorithm they talked about, but maybe this is a good place if there's any questions, something's unclear. Like he showed you this formula quite quickly over here, but this kind of illustrates the effect of the alpha. You're getting close to the average. The true average is some purple line. Your Monte Carlo algorithm will never get exactly there, but with a constant alpha estimate, you sort of get close, and depending on the value of alpha, you have a trade-off versus how fast you get there versus how close you are when you get there. And if you made alpha exactly 1 over I, you would be doing exactly the simple mean Monte Carlo. Any questions or comments before we start the example? You guys are going to recognize the example. The example is exactly the gambler's problem, with one terminal state at the top where you win and one terminal state at the bottom where you lose. So let's see the example.
All rewards are 0 except when transitioning to the upper terminal state, in which case it's 1. Also, no discounting. The initial state will be the center, and each transition is a 50-50 chance of going up or down. So one episode looks like this.
So this is the gambler going
And
up and
another?
down in his bankroll.
You get it. Now to apply constant alpha MC, we start by declaring, based on nothing, that alpha is 0.05. Next, we need to create our VS table, which we can picture like this. These are the states, and the vertical axis will tell us the table values. The algorithm starts by initializing all non-terminal state values to 1/2, though you can pick anything. In this case, it turns out you can interpret the values as probabilities, so 1/2 is a natural choice. Okay, now we sample one trajectory and apply our update rule. Okay, now if we sampled another episode, we'd get another update to the state values. And as you can imagine, the complete algorithm involves many updates over many episodes. In the end, it just bounces around the true values. So this approach works, but let's measure it. Let's look at the distance between our estimates and the true value and create a new plot. The horizontal axis will be the number of episodes we've processed, and the vertical axis will be the absolute difference averaged across the states. Now, I'll show you how things evolve with an alpha of 0.02, and if we process 30 episodes per second. This shows us how long convergence takes and provides another view of alpha. If we set it to 0.03, we'll see this. We more quickly get to an appropriate answer, but it bounces around more once we're there. If we set it to 0.01, we'll be slow to arrive at our answer, but it'll be a better estimate once we're there. This is just another view of alpha's quick and noisy versus slow and accurate trade-off. And now, finally, we're ready to move on to Monte Carlo control. Since we'll be changing the policy,
Okay, so in this example, it was exactly the problem you guys had in question 3 on lab 1, the gambler's problem. Here n was equal to 7. There were 7 states. Here the gambler loses and goes home and cries. Here the gambler wins and gets a prize car. V is the thing you answered in question 3C. It is the probability starting at some state that the gambler leaves with the prize car. If you start in the middle, it's going to be 50%. If you start close to the end, then it's higher. So that's the purple line. And the Monte Carlo algorithm that they were showing exactly bounces around this true answer.
Non-terminal
right? So,
state value update to the state value.
you start out with a guess, and then
as you
every
can
time
imagine,
you go, you're
the
using the
complete
online algorithm to
involves
update
many
these rules.
updates
And so
over
your
many
estimates, they
episodes.
bounce around.
In
and
the
their
end, it
true
just bounces
mean
around the
will
true
converge
values.
to that true average of the value
So this
function
approach works,
in purple.
but let's measure it.
But of course, you will never get
Let's
that
look
perfectly.
at the
You will always
distance
be a little bit
between
off.
our estimates
the more
and the
samples
true
you do,
value,
the closer you can
and
get.
create
And you
a
saw
new
that curve
plot.
with the error.
The horizontal
If you
axis will
look
be
at
the
this
number
error,
of
it would
episodes
be
we
the function
processed,
1 over
and the
square root
vertical
of n.
axis will be the absolute
Times some
difference
constant. So you
average
sort of get
across the
closer and
states.
closer, the more samples you do.
Now, I'll show you how
that's
things
called
evolve
Monte Carlo
with an
evaluation,
alpha of 0.02,
and it really is just taking
and if we
the simple
process
Monte Carlo
30
algorithms we
episodes
used,
per second.
applying them to the situation of estimating the value function.
This shows us how long convergence takes.
let me
It
pause
provides another
Question, yeah.
Sorry, so why would you use the alpha strategy if the policy is constant throughout everything, right? Like, because the points at the beginning are just as valuable as the points at the end.
That's right. This is so. I think one reason is in your code, then you don't need to keep track of the number of visits to each state.
Okay.
So you can kind of just as you go on any given run, you don't need to know anything about the previous runs. So you can update the value function as you go. You're just like, I was at this state, I update it by 0.02 times the difference in the returns. Whereas if you want to do a different one, then you need to keep track of how many times you visited each state, and it gets a little more complicated. But yeah, you're right. The major benefit is something we're going to see next class, which is when your policy is changing over time, then it will have a bigger benefit. Yeah. Was there another question here? Okay, so next class we're going to see Monte Carlo. Well, next class on Thursday will be the lab. When we come back from the break, we're going to see Monte Carlo improvement. So not just estimating the policy, but also improving the policy and getting even better policies using Monte Carlo stuff. Okay, so see you guys on Thursday. Make sure you bring your computer and take a look at the lab if you want to beforehand.